Suppose you have counted every word in a song. How do you find the ones that come up most often? There is a strikingly simple idea. Find the top word, cross it off, then ask the same question again. In this final part, we build exactly that, and we uncover its hidden price. First, a quick recap. In part 1, we took a song and turned it into a frequency dictionary. Each distinct word paired with how many times it appears. Our song was ra-ra, ah, rom, ma, ro, ma, ma. Counting gives us this dictionary. Ra maps to 2, ah maps to 3, rom maps to 1, ma maps to 3, and ro maps to 1. Notice something right away. Two different words, ah and ma, are tied at 3. That tie is going to matter. Here is the function that finds the most frequent word. First, it starts an empty list called words. Then it asks max for the largest value in the dictionary. The values here are 2, 3, 1, 3, 1. So max returns 3. That highest frequency is stored in a variable called highest. Now it walks through every entry using the items method, unpacking each into a key and a value. The only test inside the loop is whether that entry's value equals highest. If it does, the key is added to the list. It keeps a list rather than a single word for one reason. Words can tie, exactly like ah and ma here. So when we run it, ah gets added, ma gets added, and the function returns the pair. The list containing ah and ma together with the frequency 3. Now the real task. List every word that occurs more than some threshold number of times, ranked from most frequent down. The chosen solution is elegant and a little sneaky. It reuses the function we just wrote. Find the most frequent words, save them, then delete them from the dictionary entirely. We already know everything about them. Ask again, and the next tier rises to the top. Repeat until the frequencies drop past the threshold. Each pass peels off one layer of the ranking, like removing the top card to reveal the one beneath. Here is the function called occurs often. It takes the word dictionary and the threshold x. It starts an empty list, freq list, which will hold our answer. Then notice it calls find frequent word once before the loop. That first call exists only so the while condition has a tuple to test on its very first check. The while loop continues as long as the frequency in that tuple is greater than x. Inside the loop, the first statement calls find frequent word again on the dictionary as it now stands. That fresh result is what we append to freq list. Then for each word in it, the delete operation removes it from the dictionary. That is the mutation, and control jumps back to the top. Let's trace it with a threshold of 2. Before the loop, find frequent word reports the pair ah and ma at 3. The while test checks whether 3 is greater than 2. It is, so we enter the loop. Round 1, we call the function again, still getting ah and ma at 3, and append that to freq list. Then we delete both ah and ma. The dictionary shrinks to just ra at 2, rom at 1, and ro at 1. Back at the top, the test again checks 3 against 2, still greater, because it looks at the previous result. So we continue. Round 2, we call the function on the smaller dictionary. The highest value left is now 2, so it reports ra. We append ra at 2, then delete ra. The dictionary is now rom and ro each at 1. Returning to the condition, the test checks 2 against 2. 2 is not greater than 2, so the loop stops. Here is the subtle part. Ra has a frequency of 2, and our threshold is also 2, yet Ra made it into the answer. The reason is hidden in those two calls. The while condition tests the frequency carried over from the previous round, not the one we are about to append. So on the second round, the condition sees the 3 from before, lets us in, and then we append a Ra at 2 with no further test. The append has no guard of its own. That is why an item exactly at the threshold survives. If the code used greater than or equal to instead of greater than, the loop would run one more round and add rom and ro at 1. Which boundary is right depends entirely on the specification you were given. But this elegance has a price. Every delete permanently removes an entry, so by the time the function returns, the caller's dictionary has been guilted. It started full and ended nearly empty. The docstring does carry a side effect warning, but a warning is not a defense. Once the function returns, the counts are simply gone. That is the real cost of solving a problem by changing your data in place, and it is exactly why the same task is often written without mutating anything. Push the threshold below every frequency, say to 0, and the dictionary empties. The carried over frequency of 1 is still greater than 0, so the loop goes round once more and asks for the maximum of nothing, which throws an error. One last thing, the finished product this case study promised from the outset. Run this on the full song from part 1, hundreds of words with a threshold of 6, and the complete ranking comes back. The word I tops the list at 18. We follows at 17. Then a four-way tie, ain't ever, getting an older, each at 16. The word the sights at 15. You're at 12, then you in and that tie at 11, and the can't at 7. At the bottom, and the pull and off, each occurring exactly 6 times. The same boundary quirk we traced a moment ago, firing on real data. Step back and look at how much this one small program used. We lowercase the string and split it into words. We iterated directly over that list. We built a dictionary and populated it, counting as we went. We tested membership with the keyword in. We looped over entries with the items method and put every value with the values method. We returned tuples to bundle 2 results together. We reused one function inside another. And we mutated a dictionary with delete. Almost the entire toolkit of the course working together on a single honest problem. Proof that dictionaries earn their place as the right tool for the job. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.